I usually don't get sick very easily, but then it seems to suggest that maybe I don't know. But you guys stayed. You stayed here?
Yeah,
Okay.
most of the time.
So in Thanksgiving you went to Atlanta, but then
Yeah, the
Christmas you stayed here.
It is Christmas I stayed.
And you said,
also I stayed there.
but you said you
Yeah, I
traveled.
travel in January 4 to 7 to Florida.
Okay. And you also went to Florida.
Yeah, it was.
You were in Florida?
Yeah, for
I went to nearby places like Kentucky, St. Louis, Tennessee. But I stayed
So
in
many places?
Yeah, we're driving. I mean,
Okay.
it's not that far. Kentucky is 2
Yeah.
hours, St. Louis 2 hours,
Yeah.
Tennessee 3 hours. So I go and come keep dating.
Oh yeah, you said you bought a car recently, right?
But I didn't went with my car.
So you went with friends.
Friends, yeah.
Good. Let's see, I have to set this right. Okay. Seems to be. So we still keep this, right? And, we'll see. Oops. So yeah, was the homework due supposedly due today, but then I postponed it to next. Have you guys started the homework? Okay, so it is straightforward homework. Just do it, I guess. And, what are the courses you guys are taking?
Quantum.
This is the first one.
Yeah.
Okay. And
solid state.
solid state is Dr. Sherry.
It's actually the Zoom doc.
Oh,
Zoom doc.
okay. Oh, I see. Usually it's the Sherry.
That's what, and he was saying that he teaches for undergrad for sure, but
Okay.
this time he's teaching the graduate.
Okay. Good. Okay. So let's say homework 1. That's already posted. Let's make it due on Thursday. So that's what's the date? Let's say next homework I guess will be due on 27th next Thursday. But let me put a tentative. Sure. Let's say tentative. And we started talking about electrostatics and magnetostatics last time. Was it useful?
Yeah.
So so I'll slowly do whatever was going on last time very broadly, sort of a review kind of thing, and then slowly get into the into what we have to do this semester. So that way the notations gets clarified between last semester and this semester. So the idea was we did electrostatics last time. Let me quickly go over this. So we had Maxwell's equation, and then we split it into when there was no time dependence, then we have let's say started with the electric field is equal to rho over epsilon naught, and cross C is equal to 0. It's not equal to 0 if it was not statics, but it is equal to 0 if it was static. Same thing, magnetostatics. We'll come back to this, but it's good to see the difference. In this case, the divergence has a source, but in magnetostatics, the divergence does not have any source. In electrostatics, the curl doesn't have any source. It's curl-less in that sense. But here, curl has a source. Right? So in that sense, it's completely almost a disjoint in that sense. There is a what do you call it? There's a dual nature to that. It's not shape. So this is current. That's sorry. This is charge density. That's current density. Okay. So we'll come back to magnetostatics in a few minutes. Here, what we said was that, okay, if this is true, if curl of a field is true, that means you can write the electric field as a negative gradient of a potential. And this we compared it with a conservative force. Right? If you have a conservative force, you can write it as a gradient of potential energy. Right? So this is an electric potential, pretty much the same idea. Once you have this, so this the curl-free nature of the electric field imposes the condition, or it makes it possible that we can write it as a potential. That means that I don't have to talk in terms of electric field. Why not talk in terms of potential? Put it back in that, and I get an equation for the electric potential, rho over epsilon naught. And that's called the Laplacian. And to solve this, at least in a very generic manner, let's motivate how you do this. Instead of solving the Laplacian, you say, oh, that's a full charge density. You talk about a single charge, right? Single point charge, and that will be equal to, so this is a single point charge. Let's say single point charge. And what's the charge density for a point charge? Let me not write this yet. So there is a single point charge at position R0. Right? So this differential equation reads as, on the right hand side, some space there. On the right hand side, this will be epsilon naught. What is the charge density for a point charge? We talked about this last time. What is it equal to? What's the charge density for a single point charge at position R0?
One or in the position and zero.
It is
it's
one.
Delta function.
It's a delta function, right? It is zero everywhere except where the charge is. And that has to be infinite because the total charge has to be Q. So that gives you the idea that it's a delta function. It's Q times delta function of R minus R naught. And let's say it's not R dot, let's say it is at R prime. Okay. And that will be your electric potential, right? Electric potential due to a point charge. And let's call that the Green's function G. So this is the Green's function at R, that's the electric potential at position R due to the charge at position R prime.
So this delta 3 is because of the 3-dimension.
That's the 3 dimensions. For example, if you keep a charge here, so let's say this is X, that's your Y, so that's your X naught, Y naught, right? Let's say this is Z naught, right? So you say that the charge is at X equal to X naught, Y equal to Y naught, and Z equal to Z naught. And that's how you will say your charges. So this is your Q times this delta function. But a symbol we will use for that is Q times delta Q. And instead of saying X naught, Y naught, Y, so we'll write this as a vector R and R naught. Is that clear? Where R is X, Y, Z, and R naught is X naught, Y naught. Z naught. So this notation is the same as is a simplified, is a shorthand for that. So it's out of okay. So and this is still the electric potential. Notice I have not changed anything. This is still the electric potential, and since it's electric potential, I know what G is, right? So that implies I don't have to really solve for it, but you can solve for it. You can solve it as if it was a mathematical problem. But since we know what the electric potential due to a single point charge is, I know, oh, by the way, you also put, actually I should say, let's say this is G prime, right? Why? Because I don't want to put the Q and epsilon in there. I can scale it out there. So G, I would say, is equal to Q over epsilon naught times, sorry, the normal Green's function. Just a redefinition if you want. Okay. What that does is this becomes G. Like usually you don't have any information about charge. Okay. It's just a rescaling of Q over epsilon absorbed into the G prime. Is there any confusion there? Sure, that shouldn't be okay. Just a multiplication factor. Okay. But from this, you know what it is, right? If I compare these two, you know that that's the charge density for a point charge. That's the electric potential due to a point charge, G prime. Because of this, right? Here, this is the electric potential due to a charge density. This is the electric potential due to a point charge. So I know G prime, right? I don't have to solve for it. That's what I was trying to say, that in principle, I can solve for it mathematically, but using introductory level physics, I know that this is equal to Q or 1 over 4 pi epsilon naught Q over R minus R prime. Correct? That's a constant charge over the distance from the charge. This is the observation point. That's a source point. That's where the source is sitting. This is where you're measuring the electric potential. Is that clear?
So, I mean, I want to get the last line. You solved it, or you know.
If I had a charge at the origin, right? This is a positive charge. right? That's a positive charge. What's the electric potential at this point?
4 pi 1 by 4 pi.
1 by 4 pi r, right? So you would say it is 4 pi epsilon naught q over r, right? So that's q. If I were to place it at r prime, it is r minus r prime. Agree?
Yeah.
That's the electric potential due to a point charge. But that's exactly what this is. Right? Because that's the definition I said. Right? If this is true, whatever is the charge density, whatever it creates, that's my electric potential. Right? So the Green's function by definition is the electric potential due to a single point charge. So I can either solve for it, which we will solve. Okay. I mean, you cannot, I mean, maybe your question is, how did you go from here to there? Right? There is a procedure we can follow, like we can use, like it's not very, within 15 minutes one can do it, but we will do that in another context. But I am saying I don't even have to do that. I know the solution for that because that's what Coulomb said, right? Experimentally, I know that this is the Green's, electric potential due to a point charge. Experimentally using Coulomb's law, I know that that's what it is, right? So is that, I mean, I stated it in a different way. Any questions at this point? Okay. Okay. So if that's your Green's function, so that's good. But now you would like to solve this, right? This is your actual problem, right? I mean, point charge I already know. So I just created a Green's function problem. And the question is, how do we solve the main problem? So let's say we have negative radian square phi, and let's say this is position dependent, right? That's an observation point. Typically, I will use prime as a source point, and this is an observation point. Right? So this is 1 over epsilon naught times rho of r. Right? That's what we would like to solve. And instead, we said, oh, let me do a simpler problem, and that's g of r minus r prime is equal to, I said, delta function. Oh, yeah, so this was primed, right? If this was primed, what is g? I just had to remove q and epsilon naught from there, right? So I know that g here, it is equal to 1 over 4 pi r minus r prime. Okay. That's your two equations that we have. So we have a differential equation, and we wrote down the differential equation for another function which we call as Green's function. Okay. Whose solution I happen to know. In general, going from here to here is a good amount of work, but here I use the physics to get the solution. But now the idea is, if I know this, how can I get that? How can I get the full solution once I know a particular solution? So you can say this is a particular solution, and that's the complete solution we are looking at. Okay, clear? Okay, so to get the complete solution, what you'll do is start from the first equation and multiply g on that. So this is questions? Yes.
For the notation of the R minus R prime and the R comma R prime.
Uh-huh.
um,
Yeah, this is not very clear, right, at this point. This is. Does that help? But since you mentioned it, here also. But since you mentioned it, in general, these are comma R prime. Right? But I know the solution in this case. I know that it is R minus R prime that it depends on, right? And generally what happens is that if you have a function like this, and if you have just one point, like there is a source solution for this depends only on one point in the universe. If there is no boundary, how can it know where that point is? I should be able to translate it and still the solution will remain the same. It's like saying in this whole universe, if you are the only person sitting, if you move one step, the universe will look exactly the same. Right? So that's the idea in that there is a translation symmetry. If there is no boundary, close by, that means to say that if you have a metal sitting there, like if there is a point charge right in front of a metal, then that symmetry is lost. And then you have to work extra hard. So then you cannot use that symmetry. R and R prime being. In our case, it is going to be the case we are not going to, like those were problems that you probably came across. There was this method of images that you used to get it. Those are all problems that can work with using these methods, but we won't be going back and work on those problems. Here, let's just motivate the idea of Green's function. Let me broadly say that there are what we are doing is there is a lot of point charges giving you a density of charges and what is the electric potential. If you have a lot of point charges, how do you find the electric potential? You just add them, right? That's the superposition principle, right? If you know the solution for one charge, the solution, you know the solution for the second charge, the total will be just add them together, add these two solutions together. That's called the superposition principle. And what I'm going to do is basically derive the superposition principle. Usually when in introductory level physics, we just assume that, but here in a few lines, I'm just going to derive the superposition principle. If there are no boundaries, if there were boundaries, superposition principle changes. It's no more sum of two charges. The boundary can affect the charge. As simple as that would be a reflection effect on it. Okay, so that's what we are going to do. And I think, yeah, at this point, I should be having this as R, right? No, R. I think it's just, yeah, since we are just reviewing, let's not worry too much about this. And let's just keep this as R minus R prime. That leads to some simplicity in the analysis. Otherwise, one just has to be careful about where R and R. So let me go ahead and use the fact that it is R minus, it depends only on the distance between them. That way, the main idea is that I can switch this now, right? I can write this as R minus R prime or R prime minus R. It plays an important role again when there are boundaries. When you have boundaries, you do not have that symmetry and you cannot do that. Any questions at this stage? Okay, for all, okay. So I had, this was the equation I was interested in. Instead of this equation, I started from point charge, which is a Green's function. Then I multiplied the solution to that, and notice that I know the solution here, right? But I am interested in phi, and that's what I would like to solve for. So let me integrate. Let me integrate this over R in cube. So this R is what I'm integrating on. So or on the right hand side also I integrate over R. Since I'm integrating over R, which is the observation point, I should rewrite in the end. I will switch my variables. Okay. Okay. Let me, this is, so I'm going to use integration by parts. Remember, maybe I should point that out. If you have an integral dx f of x derivative of g of x, right? How do you integrate by parts? Let's say this is v to b. You would say that this is u, this is v, right? That's how you would do that. But instead, what I'm going to do is it's the same thing, but I will do it slightly differently from what you're probably used to, and that's going to be the following. Right? This is d by dx of f of x. Is that correct? No, right? It's not. Immediately now, because the derivative is acting on your g. Here, the derivative is acting on both f and g. So this is wrong, right? But I can fix this by subtracting whatever is the mistake. So let me fix this by subtracting out whatever I made a mistake of. So here that is, it's acting on f also. So I just subtract that out. Right? It is d by dx of f times g. Is that clear? Right. That's just distribution of derivative, right? Here it acts on f. That's your f, subtract that out, and whatever is remaining is a g. Correct. So, if that's the case, this is a total derivative now. D by dx of d by dx, that's a total derivative. Dx cancels out, that's total derivative. So, this contributes only at the boundary. Right. So, this has led us to say that g of x evaluated at x equal to b and x equal to a, and this is same a to b dx f of dx times g. The way you would have done probably is that this is typically written as this is u and this is b. This is b prime, right? Say this is u prime. Yeah, so this is u and this is b prime, suppose, right? That's how you will write this. And this is equal to u v at the boundary. So this is a b minus of dx. This is u prime. Right, that's how you would probably remember this from whatever. But notice it's the same. I didn't do anything different. It's just I didn't try to remember this. I just tried to do that in my head. Okay, that's in one dimension. And notice what is happening. If it's a one dimension, this is a line integral. And a and b is the boundary of that line. Right? If you have a line, this is a, and that's your b, that's your boundary, right? So the way to interpret this is that you get a contribution at the boundary, and you do get a bulk integral, which is SWIFT, which swaps. So now let's do this in 3 dimensions. Let's integrate on a volume. So let's say this is f of r. And now instead of d by dx, I have a gradient. And this is on a volume. And that volume can have a surface. Like every volume has a surface enclosing that volume, and it could have broken surfaces also. Is that clear?
Yeah.
Okay. So using this analogy, what we will do is, now this is, instead of saying this is evaluated at A and B, we will say this is evaluated on the surface. Right, so I have to say that this is equal to, this is a vector, notice, so that's the A, right, that's on the surface, and you have f of r, and on the surface. So this is now, if you want, it's a closed surface, right? This is S. Right, this is the surface enclosing the volume V. Right? And minus of